So, let me now jump to the case of, or go to the case of 2 discrete random variables, right. And it is always better to start with some omega. So, it is always, even though you can say, well, later on you can sort of dispense with this omega in some sense and do a direct specification, in which case, right, you do not talk of an underlying experiment, but for the time being let the omega come into the picture, because it is very important right now. So, we are interested in, of course, we are not jumping into the continuous case right now, we are still going to stick to discrete, right. We are interested in the joint behavior of 2 discrete random variables, that is very important, right. What is the probability that x will take some value and y will take some other value at the same time jointly, as a joint event? That is what we want, and it turns out this joint event is the key to understanding the joint statistics of 2 discrete random variables. Right. You do not look at x and y in isolation, you look at them together, and so the specification will need something much stronger than just a simple univariate PMF, right. Whatever we have talked about so far, the PMFs are all univariate, they just depend on one random variable. So, this is going to take us to the bivariate, to 2 PMF with this joint, to bivariate PMF. So, how do these arise? I mean, clearly we will look at many examples, but just let me do an abstract thing, right. Supposing I have some omega here, I have, let us say it is a discrete omega, just for simplicity, right. The same idea will apply even when omega is continuous, but so the basic thing sinks in, right. So, I have 2 axes here that define x and y. So, these are the names of my random variables x and y, right. I have already said in some previous lecture that you can define more than one random variable on a sample space, right. I am pretty sure I said it, right. If I did not, if it is not, if the significance of that did not sink in then, let it sink in now, right. It is clearly possible to define many random variables depending on the experiment. I think I did say it yesterday, right. If I pick a person at random, there are many umpteen numbers that a person carries around, and each of them is a separate random variable. So, we are only interested now in the case of a discrete sample space omega and two random variables x and y. So, this is a point omega, consider any sample point small omega in capital omega, right. By the mapping, right, x mapping, it maps to, this is x of omega and this is y of omega, right. This is by definition, right. If you define 2 random variables, and clearly both x of omega and y of omega must be defined, and both of these are numbers. So, this is a number axis, this is a real line, this is another real line. Now, what you are going to do is look at the collection of all these pairs of points. What is that, and the commonality, I mean the fact that these two are not happening separately but happening together. Whenever you observe this sample point small omega, you are going to observe this value, this is going to be the output for x and this is going to be output for y, you have no choice in that. If you pick a person at random, you can't say I am going to pick the height of this person and the weight of that person, that is completely wrong. You have to go with that omega if you look at joint behavior. So, let this sink in again, it is very crucial, right. Without this understanding, your whole you cannot understand how 2 random variables behave, right. The fact is that you are looking at jointly what values they take, not just separately. If you, as I said, you can also close your eyes to y and only look at x, that is back to the univariate situation we have been talking about all this while, but we need to make the conceptual jump now to at 2. So, this is right, one joint pair, this is another joint pair which I am just leaving, and then you can have one more here. So, if you collect all these for the discrete case, if you collect all these pairs of points and put them on the plane, what will you get? You will get a countable collection of points in the xy plane. So, this is small x and y. So, this will be what? Possible values of, or let me just write this as the collection of x of omega, right, and this will be, and because I am viewing it as countable sets, I can use this braces notation, right. So, the collection of x of omega, if I therefore put a point here, this is going to be, I have the coordinates x of omega, y of omega. Now, let us say I do it for all possible points. So, what will I get? I will get some grid, some collection of points which in many cases falls on a nice grid, some integer grid maybe. Right. So, this collection of points, right, is the fundamental starting point for studying the joint behavior of x and y. Note, we cannot look at just the point, the values of x alone or the values of y alone. You have to look at, and you cannot associate this x coordinate with the y coordinate of this point. So, that is why it is better in the beginning to not to draw it as a regular grid, but to randomize it enough so that, right, you realize that this point is uniquely specified by this value that x takes and the value that y takes. This is clear to everybody? Does anyone have any questions? Remember, once again, last time I will say, you cannot arbitrarily combine the x coordinate of one point and the y coordinate of another point. That completely violates the whole mathematical structure of what we are trying to do. Okay. So, this is the set omega, what we are going to call as omega xy. This is a countable subset of the plane, and the plane we write as r squared. The line is r power 1 or just r, right. The plane is r squared. What is omega xy? Omega xy is a set of all possible values that x and y can take jointly. So, how did I write it here? Let me, since I have already written it and brought it here, I do not want to, I just want to, for the sake of this, just just write it as x. Okay. Doesn't matter. So, maybe I won't write it here because it's possible that it might not come out so well in the video. So, omega xy is essentially defined to be x omega y omega for all omega, small omega and capital omega. Just think of it like this. This is a qualifier, colon. Some people use a small vertical line here, but since we have been using vertical lines for conditional probabilities, I am using a colon. Colon is also used as often as a vertical line here. So, you vary this omega, small omega for all points, you look at jointly what happens to x and y. So, this is starting point for this joint specification. And when the sample space is when capital omega, sorry, which I have written it here, when the underlying sample space is discrete, there is no way that this omega xy is going to be anything other than countable. It has to be countable, right. How many points? Supposing I have n points here, I can only get totally n points here. I cannot get more. I can get less, but I cannot get more. Okay, if I have a countable infinity of points here, I may be able to get a countable infinity, that is a different issue, right. But basically there is, you can say a one to one correspondent, I mean maximally a one to one mapping between these omegas and these points. So omega xy has to be countable. So what about the probability now, right? So supposing this is the point, instead of writing capital X omega y omega, we need to have some more notation for the point. So now supposing you consider some xy, a point xy in that set. Right? You consider this point xy in that set. So then you look at the joint probability that of x taking the value x and y taking the value y, right, jointly. So that is the, if you repeat that over all these points x, y, you get the joint PMF of x and y. Right. And you indicate the two random variables with a comma, right. This is the probability that x, so it's a joint event, right. And you repeat it for all, you do this, if you write out these probabilities for all x y in the countable subset omega x y. If you do that, you specify the joint PMF of x and y. Okay. So what properties do you have now? So that, which implies that this Pxy has to be between, although you can say why should it be 0, it obviously, I mean we are anyway, let us not split hairs over it, but let us say it can take, you can go up to 0 and up to y equal to 1 also does not make any sense, but does not matter, we will just put it here. So but okay, this and this summation over all, and I want to write it as a single summation now, not double summation. If I add it over all points omega of small xy, I will get what? I should get 1. Otherwise, if I go here and look at the probability of this point plus probability of this plus probability of this, they all must add up to 1. They all have to be non-negative, they have to add up to 1. So these are the basic rules with which we operate. What, and again the meaning of this Pxy x comma y, note the notation. You write the random variables subscripts in some order, right, and I am going to dispense with the comma in between. Some people put a comma here, I am not going to put that comma, right, just xy. If I have 3 random variables, right, I can write them as xyz or x1, x2, x3 whatever without commas. Then I have the same number of arguments as I have random variables, and the first argument is the value taken by the first random variable, the second one by the second random variable in the subscript, and so on. That is the convention that we use, right, and this again is a joint event always. This event is is exclusive of any other point, right. xy, x1 y1 is automatically exclusive of x2 y2 or x1 y2, assuming that x1 y2 is also in the set. So if you have a regular grid, obviously you will you can draw a vertical line and or horizontal line, you will find more than one point on that on any given vertical or horizontal line, right. And supposing it is an integer grid, as we will see, just we do an example, like I am running out of time, so pick up the example in Tuesday's class, right. But for now x1 y1 is unique by itself, or is an entity by itself, right. It is exclusive of x1 y2 or y1 or x2 y1 or any other point, right. And we are interested in this joint probability always, right. The starting point is we have x and y jointly taking values what set. Idea is they jointly take values in the countable set of the plane, right. R squared is the xy plane, and omega xy is the set in which they take they take values, and the key point is omega xy has to be countable, right. There are only finite number of points in that, countable number of points in that set. You cannot have, for example, the whole unit square 0 1, for example, that would be straight away an uncountable number of points, okay. So this is omega xy, and then you have the joint. So the joint PMF is basically a collection of joint probabilities. What these are all joint probabilities of the type of what events? X equal to x, y equal to y, and y equal to y for all x y pairs inside omega xy. In other words, i.e. the notation we write Pxy x comma y is the probability of this event, right. Any questions on this? This is very crucial definition, right. So this is our atomic event now regarding these random variables x and y, and we are looking at this joint probability, x takes the value x and y taking the value y. Remember, when you do the experiment or when you have one run, you must get a value of x and you must get a value for y. So this kind of joint event is obviously what we should be looking at. So if you go back to that picture which we drew, we have a point small omega and capital omega which is mapped to one point for x and a different point for y, and you are looking at when that point omega occurs, that x and y occur together. So that is the joint event that this is. Note also, you can get multiple points in capital omega mapping to the same value x and y, that is entirely possible. Okay, so I think the best thing to do is to look at some simple examples. Let me make sure that yes, I think we are ready to look at examples, no point in rehashing. So if you do this, right, the joint PMF, okay, I have to complete the mathematical specification, I will do that and then go to the examples. So if you do this for all points xy in omega xy, then you have specified the joint PMF. So what are the properties of the joint PMF? It's basically a collection of joint probabilities. So the double summation of omega p of xy must be equal to, well, or single summation, I do not know, maybe last week I wrote it as a single summation, but it is sometimes, right, written as a double summation, it does not matter. So this is for, if you add it, right, if you add all these probabilities, you must get 1. So that is the most important, I mean, that is the key idea, that you have not left anything out. No possibility with finite probability must be left out in the specification of the joint PMF. Obviously each of these probabilities must be between 0 and 1 also.